Hello all. Yesterday we have seen digital electronics, the basics fundamental concepts of digital electronics. We've also seen how digital electronics or digital circuits are different from analog electronics or analog circuits, right? So we have seen, yesterday we have covered the basics of digital electronics starting with logic gates. We have seen three different classes of logic gates, and then we've also seen some Boolean algebra concepts, that is the Boolean algebra laws. We use all the Boolean algebra laws in designing the digital logic circuits. So today's session we will be discussing about few more concepts. We will be looking into how do we design digital electronics, digital circuits. So before we actually start dealing with designing digital logic circuits, we have few more other concepts to cover. So that is what the agenda for today's class. Okay, next. So today in the session we are going to cover these three topics. So one is all about sum of products, second is product of sums, and the third one, the most important concept of digital circuits, which is K-maps. Okay. So in the last class we have seen there are three most important operations that we have to look into to design any digital logic circuits using Boolean algebra. That is the inversion operation or the complement operation, and AND operation or the multiplication operation, and the last one is or the addition operation. So using these three operations we are going to design digital logic circuits with these concepts into consideration. Okay. So the first thing is we are going to look into sum of products. The name itself says we are adding or ORing the product terms. Okay. So in order to get a function, Boolean function, so when we have discussed about the Boolean algebra terminology yesterday, we have looked into what is Boolean function, right? So I told you ORing or ANDing of the variables will form a Boolean function, right? So yesterday we have seen an example of Boolean function. Let's say if I take f as a variable for Boolean function, I may write a Boolean variable as ab bar plus a bar b, or I can also write a Boolean variable as a plus b into a bar plus b. Okay. So these two are different Boolean functions. Okay. When we look into these Boolean functions, what I observe in this particular function is this function is the sum of products. Okay. So this is my first product term and this is my second product term. So I call these as product terms and I am summing them. So this particular representation of this Boolean function is called as SOP, sum of product. And when you look into this particular Boolean function wherein I have a plus b into a bar plus b, that is, this is one sum term and this is another sum term. Okay. So I am producting these two sum terms. So this type of representation is called as product of sums. Okay. Not just about the terminology, we are going to look into various aspects or various representations of POS form and SOP form, which plays the major role in designing digital logic circuits. Okay. Apart from these two, we are also going to study about K-maps today. Next. Okay. Now first let's look into SOP. SOP, sum of product, is the abbreviated form of SOP. SOP is a form of expression in Boolean algebra in which different product terms of inputs are being summed together. So as I have shown you here, different product terms of inputs. Here the inputs are A and B, right? So the different product terms of various inputs are summed together. Next, before we actually start with minimizing the expression or understanding the concept of the Boolean function, we will also look into two most important terms which are called as min terms and max terms. Okay. So first let's discuss about what min terms are all about. Okay. As you can see, min term basically means the term that is true for minimum number of combinations of inputs. Okay. So basically we get minimum number of combination of inputs for AND gates, right. So AND gate gives true only when all of its inputs are true. So that is the reason we get minimum number of terms when the output is true when we use AND gate. So basically these product terms that we are discussing are called as min terms. Please make a note of this. When you take any Boolean function, we have two different representations of Boolean function. One is called as sum of product and the second one is called as product of sums. So when we take sum of product into consideration, it is all about ORing. It is all about adding all the product terms, and this individual product term that I am taking is referred to as min term. Okay, the product terms in Boolean algebra are called as min terms. Okay, now next. So yesterday in the class we have seen how do we generate different combinations of values from two inputs, right? Let us quickly recap about it. So when we have taken two inputs A and B, okay, so when I take two inputs A and B for Boolean algebra, so we have two input combinations. We have two inputs 0 and 1 for which we generate four different combinations, right? 0 0, 0 1, 1 0 and 1 1. This was yesterday's session where we have discussed about how do we get these four combinations from two inputs, right? So now let's apply the same logic here and try to generate the different combinations of inputs for three variables. Okay, so as you can see here, I have three inputs A, B, C. When I have two inputs, I have four combinations 0 0, 0 1, 1 0 and 1 1. The binary representation of inputs here. Okay. Now when I take three input variables A, B, C, I have these combinations starting with 0 0 0 and ending with 1 1 1. Okay. The binary representation of the number is actually given there. For example, if I want to take the binary representation of 6, okay, what do? We divide it by 2. 2 3s are 6, 0. Next 2 1s are 2, right? Okay, so 1 1 0. 1 1 0 is the binary representation of 6. All of you know this. So here we are representing the same thing here. Okay, so 0 0 0 stands for 0 number, 0 0 1 stands for 1, 0 1 0 for 2, 0 1 1 for 3, 1 0 0 for 4, 1 0 1 for 5, 1 1 0 for 6, 1 1 1 for 7. Okay, when I take number 7, okay, so when I divide it by 2, because we have two binary numbers 0 and 1, so that is the reason I am dividing it by 2. So I have 2 3s are 6, 1 and then 2 1s are 2. Okay, so this is 1 1 1. So 1 1 1 to the base 2, 7 is equal to, the number 7 is represented with what? 1 1 1 1 in 1 1 1 in binary. Okay, so this is how I generated 8 different combinations for 3 input variables. Okay, now when you look into this, when I say 0 0 0, okay, so when I say 0 0 0, this A input is 0, B input is 0, C input is 0. So as I told you earlier, the 0 terms are represented with complement. Okay, so I represent this A, B, C when they are 0 0 0 as A bar, B bar, C bar. Okay, so this is one product term which I call it as min term. So when you look into this truth table here, I have 0 0 0 represented as A bar, B bar, C bar, which is one min term. 0 0 1 represented as A bar, B bar, C. Okay, as I have C variable as 1, I have removed the complement. Okay, so I represent the 3 input variable 8 combinations in min terms like this, and the corresponding designation I give them as M0 to M7. Make a note of the small m here. Okay, min terms are represented with small m. Okay, min terms are nothing but the product terms which represents one product term of the given input combination, and they represented as M0 to M7 if you go for 3 input variables. Okay, now if I want to represent 4 input variables, what do we do, guys? If I want to go for 4 input values, what do I do? Let's say I take 4 inputs as A, B, C, D. Okay, so how do I represent? 0 0 0 0, 0 0 0 1, 0 0 1 0 and so on till 1 1 1 1. So this will be with 0, 1, 2 and so on. When I go for 4 input variables, I will have 16 combination, 2 to the power of 4. So I will have 0 to 15. Okay, so all these 16 input variables for which I have the designated minterms as A bar, B bar, C bar, D bar, A bar, B bar, C bar, D, A bar, B bar, C, D bar till A, B, C, D, which will be designated as M0, M1, M2 till M15. Are you clear? So, you can take 2 input variables, 3 input variables like what it is displayed here. You can also take 4 input variables like I explained. You can also go for 5, 6, 7 or n input variables. Okay. So, basically understand that minterms are nothing but the product terms which are designated with small m suffix 0. So, if you are taking 4 input variables, you will have M0 to M15, 3 input variables M0 to M7 and so on. Next. Okay. Now, when we talk about the sum of products, okay, we are still in sum of products or minterms. Okay. So, when we are discussing about the sum of products or this thing, we come across this term which is called as canonical SOP form. Okay. Now, this canonical SOP form represents the Boolean function with activated minterms. Okay. Now, let me explain you. As you can see, this is the standard canonical form is basically the standard form of sum of product. Okay. Now, this is formed by ORing the product terms. When you are forming the Boolean function, like I explained you, when you form the Boolean function and or the product terms, that is called as canonical SOP form. Basically, sum of products A bar B plus AB bar. If I take these two literals, okay. Now, this is one product term which is called as minterm. This is another product term which is called as minterm. ORing these two product terms into a sum of product, that is A bar B plus AB bar. This is called as the canonical SOP form. Okay. The Boolean function which is formed by ORing the product terms is called as canonical SOP form. Okay. Now, how do we represent this? If when I say this, you are ORing the product terms, you say that is similar to a Boolean function. No. So, we have different representation of it. So, we use this particular symbol. Okay, we use the summation symbol and give the minterms with comma. Okay, so whenever, see, whichever the minterms are activated, so those minterms are represented and given as summation of the minterms. Okay, now let me show you that. Next. Next. Okay. Now, when you look into this particular truth table, this is an example given for you to understand what is a canonical SOP form. Okay. When you observe this particular truth table, how many inputs do we see here, guys? We have A, B, C. Okay. For which the combinations are from 0, 0, 0 to 1, 1, 1. Okay. Now, when you look at this particular truth table, we also have another column which represents the function f. Okay. Now, when you see this particular function, I have combinations of few zeros and ones. Okay. Now, when you are talking about minterms or canonical SOP, I am interested in the ones. Okay, where the output variable is represented with ones. Okay. Now, where are the output variable represented with ones? This is 0, first column, second column, third column, fifth column. So, 1, 2, 3 and 5 columns I have ones represented. Therefore, I write my canonical SOP form as f is equal to summation of 1, 2, 3 and 5. Okay. How did I get those 1, 2, 3 and 5? Looking at the output variable. Okay. So, f is my output variable wherein I have 1 here, 1 here, 1 here and 1 here. That is, in first, second, third and fifth locations I have my output variable as 1. Hence, I am representing my canonical SOP form as f is equal to summation of the given minterms which are high, that is M1, M2, M3, M5. Okay. Or else you can also expand this summation and write the Boolean function as M1. What did I tell you? M is nothing but, small m is nothing but the product term. ORing the product term is the canonical SOP form, right? So, M1 plus M2 plus M3 plus M5. You can also write it in this way or you can write it in this way. Okay. Now, what is the expanded form of this expression? What is M1 here? M1 is nothing but A bar, B bar, C. As they are zeros, I am considering them as bar. A bar B bar C plus A bar B C bar A bar B C bar plus A bar B C plus A B bar C. That is what is given here. Okay. So you can go for any of the three representations which are given here. Okay. You can go for F is equal to summation of M1, M2, M3, M5, or you can write F is equal to M1 plus M2 plus M3 plus M5, or you can also write it in the expanded min-term representation. Okay. So this is all about your sum of product or canonical SOP form. Okay. Now minimal SOP form. Okay. When you look into this canonical SOP form, it is just the representation. It is just the representation of your truth table. Okay. But when you deal with designing digital logic circuits, when we are actually dealing with digital logic circuits, always remember, like I told you in the last class, we are more interested in advanced technologies, right? We want very sleek devices. When you look into the electronics era when you were kids, okay, when you look into the electronic devices that we are using now, we get very complicated compact devices, right? We get very compact, very slim, and easy to use devices. All this revolution took place when you start using the less number of components. Okay. So when you are designing a digital logic circuit, not just generating the expression but trying to reduce that expression. What will happen when you reduce the expression? When we reduce the expression, the number of variables or the terms that we use will be less. When the number of variables or terms used are less, obviously the number of components that we use for designing the digital logic circuit will be reduced. Okay. So not just learning the SOP form, we also have to generate the minimal SOP form. So how do we do this? The minimum SOP form can be generating by applying your Boolean algebraic theorems or by K-maps. So as I told you, today in the class we are going to discuss about SOP, POS and also K-maps, right? So using Boolean algebra theorems that we have discussed yesterday and using the K-maps that we are going to study today, we are going to reduce the Boolean function such that the number of literals or terms that are used in the expression will be reduced, which will reduce the size of the digital logic circuit, with which the cost of the device and the processing time for the device and the area occupied for the device will be reduced. Okay. Next. Okay. So this is how we reduce the given Boolean expression. We will understand this or study this in detail when we discuss about K-maps. Okay. Next. Okay. Once we are done with SOP, the next term that we are going to study, next topic that we are going to study is all about POS. Okay. Now this is interesting. POS is nothing but product of sums. Okay. The name itself says POS is nothing but the product of sums. So what do you understand from this here? Product of sums. What do you mean by that? Anding the sum terms. Okay. So when I take the Boolean expression, something like this. Okay. So A plus B bar into A bar plus B. So what am I doing here? I am producting the two sum terms, right? So each sum term is basically called as max term. Okay, the product term was min term and the sum term here in this expression is called as the max term. Okay, look at that. The product of sum form is a form in which products of different sum terms of inputs are taken. Okay, these are not arithmetic products but they are logical Boolean and or respectively. Okay, now to just understand that the product of the sum terms is nothing but your POS. Okay. Now, so as we have seen, we have represented the min terms with summation, right? We have represented a min term something like this, right? M1, M2, M5, M6, something like this. Okay. So for max terms, we use the symbol pi. Okay. Summation here, pi here. This is for min terms, that is SOP. Okay. So when you are taking the max terms, that is POS, we use this pi and we use this capital M. So M1, M2, M5 and so on. Okay. So Min terms are represented with small m's, which are product terms. Max terms, which are sum terms, are represented with capital M. Okay. Now look at this. Look at this, same thing again. I am taking 3 variables A, B, C, 8 different combinations of 3 variables starting with 0, 0, 0 to 1, 1, 1. A plus, look at this, sum terms, right? We are talking about sum. So here you have to observe that 0 in the sum term represents not complemented, 1 represents complemented. Please make a note of this, okay? Don't go, see, this is where student gets confused. Don't go with 0 is equal to A bar, okay? That is for min terms. When you go for max terms, 0 is A, 1 will be A bar, okay? Now look at the notations. When I have 0, 0, 0, the max term would be A plus B plus C. When I have 0, 0, 1, the max term will be A plus B plus C bar. When I go for 0, 1, 0, I have A plus B bar plus C. When I have 1, 1, 1, it will be A bar plus B bar plus C bar. That is 0 represents the original literal, 1 represents the complement of that particular literal here in max terms or in your POS. Okay. Now they are designated as M0 to M7. So basically you just understand that if I am taking 0, 1, 2, 3, 4, 5, 6, 7, 8, okay, if it is a min term, it is a product term where 0 is represented as 0, 0, 0, which will be represented as A bar, B bar, C bar. Okay. Similarly, when I take the max term of it, okay, so this will be represented as A plus B plus C. Please make a note of this particular point, okay. So when it is 0, I have 0, 0, 0. The min terms are product terms which are represented as A bar, B bar, C bar. The max terms are the sum terms which are represented as A plus B plus C, okay. Now let's take another example, 5. 5 is 1, 0, 1, okay. So how do I represent it in min term? A B bar, C. How do I represent in max term? A bar plus B plus C bar. Did you all get this? So 1 represents the original literal, 0 represents the complement when you take as min term. But when you take max term, 0 represents the original literal, whereas 1 represents the complement of that particular literal. Okay, the same thing is what represented here. Okay. Yes. Minimal POS form, the same thing again. Okay. When you want to generate compact digital circuits which process at high speeds, which takes very less space, which which is reducing the cost because of less components used, we have to reduce that particular expressions using K-maps. Okay, next. Yeah, so this in short. Okay, so 2 variable. Okay, I have taken 2 variables. If I take 0, 1, 2 and 3, 0, 0, 0, 1, 1, 0, 1, 1 combination. Min terms, x bar, y bar, x bar, y, x, y bar and x, y. Max terms, 0 represents the original literal with sum operation and this one. Okay, so this is a min term and max term representation for 2 variables with which we have 4 combinations. Okay, now min term function example. Okay, so as I already told you, 0, 0, 0, 3 input variables x, y, z starting with 0, 0, 0, 1, 1, 1, which are indexed from 0 to 1. Look at this expression, if suppose I have this function, what is a function? X bar, y bar, z plus x, y, z bar plus x, y, z. Okay, now they have 3 variables, okay, 3 terms here. Okay, now first of all tell me, I have product terms. So this is sum of products, sum of the products equation. Okay, now I have one x bar, y bar, z. Okay, so x bar, y bar, z is this one. So M1 is 1 here. Next I have x, y, z bar which is M4 and I have x, y, z which is M7. So wherever I have these variables, I am putting them as 1 and the rest of them as zeros. So what is the function here? F1 is equal to summation of M1, M4 and M7. right? Summation of M1 comma M4 comma M7. This is your SOP min-term function example. Okay. Similarly, let's look into max term. Okay. Now look at this. How am I representing max terms? Product of sums, right? M0. So when I have M0, how do I represent? X plus Y plus Z. Okay. So M0, M2, M3, M4, M5. This is how I represent the function. Okay. So this is all about your sum of product terms and product of sum terms. Okay. Now, so far we have seen what are digital circuits, and then we have also seen logic gates, we have also seen Boolean algebra, and then we have also seen Boolean function, right. So using logic gates, after logic gates we have designed Boolean function, and then we have also seen two different forms of Boolean functions, SOP and POS. We have also seen what is canonical form of both SOP and POS. Okay. As I was telling you, not just getting the function, but trying to reduce the function is the most important aspect of digital circuit designing. Okay. So in order to make the circuit faster, in order to make the circuit at low cost, in order to design the circuit with less space, we need to shrink that particular digital logic circuit, that is reduce the digital logic circuit. So how do I do that? Okay. So one method is you can directly apply Boolean algebra. Okay. You can directly apply Boolean algebra and reduce. But the problem is we doesn't know where exactly which law should be applied. First thing, and secondly, we will be not sure if the reduced expression is the final one, or is there any possibility that we can still apply few more Boolean laws and generate the reduced expression, right. So we are not sure, because one will apply one theorem, the other person may apply the other theorem. Okay. The reduced expression of two different people would be different if you apply different theorems and Boolean laws. Okay. In order to avoid the second alternative, in order to avoid this, the second alternative to reduce the Boolean function is by K-maps method. Okay. K-map stands for Karnaugh-Map method. Okay. Now, basically we can go for algebraic procedure for reducing the Boolean expression, as I told you, but it is very difficult to apply in a systematic way, and it is difficult to tell when you have arrived to a minimum solution. As I told you, we will not be sure if I go for 100 variables. Okay. If I go for 26 variables, say A to Z. Okay. If I have 100 literals in each variable. Okay. So I am taking 100 literals in each function. Okay. So I am not sure what laws to be applied, or if the expression that I get at the end is the optimal solution or not. So that is the reason, in order to avoid the complexity of Boolean algebra, we go for this next method, which is called as K-map method. Okay. Now we can use K-map method to minimize the function with up to 6 variables. Okay. A, B, C, D, E, F. Okay. You can take up to 6 variables with n number of terms in it, and you can reduce that with the unique optimal solution using K-map methods. Okay. So here we will be applying either SOP form or POS form in our K-maps method. Okay. Next. Okay. Now, what is this K-map method? The Karnaugh-Map method provides a systematic method for simplifying the Boolean expressions. Okay. If properly used, they will give us the simplified POS expression. Okay. POS or SOP expression, such that we will be getting a simple digital logic circuit without the functionality being disturbed. Okay. Now, how does a K-map look like? What is this K-map? How does it look like? Okay. So it is, at the look, it looks like truth table, but instead of rows and columns, we have this array representation for a K-map. Okay. So depending upon the number of variables that we take, we have number of cells in the array representation of K-maps that we are going to see today. Okay. Now, the cells in this K-map are arranged such that simplification of the given expression is simply done by grouping the cells. Okay. I will explain you how do we represent this K-map and how do we do the simplification of the Boolean expression using K-maps today. Okay. Next. Okay, now this is the procedure. I want all of you to look at this. Okay, so this is the procedure for solving an expression using K-maps or for reducing the given expression using K-maps. Okay, so I have put that into 6 steps. Let me explain you how do we do that. Okay, first thing is, first select the size of the K-map depending upon number of variables. Okay, so as I told you earlier, K-maps can be used for solving or reducing the given Boolean function for up to 6 variables. That is, you can take 2, 3, 4, 5 or 6 variables. Okay. Now when I take 2 variables, the number of cells that I take will be 2 power n. Okay. So if I take two variables, it will be 2 power 2, that is 4 cells. So for 2 variable K-map, I will take 4 cells, something like this. Okay, so this will be the 0th. See, for 2 variables I have 4 combinations, right? 0, 0, 0, 1, 1, 0, 1, 1. So I will take it as 0, 1, 2, 3, 0, 1, 2 and 3. So this is 0, 0, 0, 1. This is 1, 0, 1, 1. 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3. This is a 2 variable K-map. Let me take the 2 variables as A and B. Okay. So first step is select the K-map according to the total number of variables. Okay. So if I have 2 variables, I will have 2 power 2, 2 power n, where n represents this. Okay. So when I have 2 variables, I have 4 cells which I arrange it like this. Okay. Next, identify min terms or max terms as given in the problem. If suppose I have my expression as f is equal to ab plus a bar b bar. Okay, this is my Boolean function wherein I have 2 product terms. Okay, so ab and a bar b bar. This is SOP, product of terms, right? Sum of products. Okay, now ab is nothing but 0, 0, a bar is nothing but 1 and 1. So in this particular function I have 2 terms, 0, 0 and 1, 1. This is 0, 0 and this is 1, 1. Okay, I will identify the min terms. I have 2 min terms which are 0, 0 and 1 and 1. So that is your step 2. Okay, next, for SOP, put the ones in the blocks. This is SOP, right? So I am putting ones in the block. If suppose I have POS, I will put zeros in the block. Okay, with respect to the min terms. For POS, we will put zeros in the blocks of the K-map with respect to the max terms. Okay. Next, make rectangular groups that contain the total terms in the power of 2 such that 2, 4, 8 are trying to cover as many number of elements as we can do in the single group. That is, in short, after we place these terms, we are going to perform grouping. We are going to perform grouping. Grouping of 2, grouping of 4, grouping of 8, grouping of 16 and so on. Okay. First priority should be given to the highest grouping. When you go for highest grouping, you will be getting the least expression or the least reduced expression. So first check the possibility if you can group 16. If that is not available, go for grouping of 8. If that is not available, go for grouping of 4. If that is not available, go for grouping of 2. Don't go in this way, this is wrong. You have to check for grouping from the highest number of variables that you can group to the lowest. Don't get confused, I will explain you, just remember this. Okay. First thing is, choose the K-map depending upon number of cells. Second thing is, place your min terms or max terms inside that, and third thing is you have to perform grouping. Okay. Next, after you are done with that, form the groups that have created in step 5 and try to find the minimum SOP form. Once you are done with grouping, we will try to give the expression for each group. Expression for each group. And finally get the reduced Boolean function. Is that clear, everybody? So first we'll take, depending upon the number of variables, we will take the number of cells, arrange the cells, place your minterms and maxterms depending upon the problem given, and then perform grouping of two variables 4, 8 and 16 only. The priority should be given for 16 grouping to reduce the expression to as much as you can. If that is not possible, go for 8 grouping, 4 grouping or 2 grouping. And after you are done with the grouping, you have to generate the expression for each grouping that you have done, and then that will be your reduced Boolean function. Now look at this. 2 variable K-maps. When you go for 2 variable K-map, as I told you, 2 power 2, that is 4 variables, 0, 0, 0, 0, 1, 1, 0 and 1, 1. Here you can represent them as what? 0, 1, 2, 3, or you can also represent them as what? A bar, 0 is A bar, B bar, right? For product, A bar, B bar, A bar, B, AB bar and AB. Also you can represent with minterms M0, M1, M2 and M3. Okay. So this is 4 cells for a 2 variable K-map wherein I have A input and B input. Okay. Now, as I told you, first is checking for the cells, drawing the cells depending upon the variables, and after I draw that, now I will take the expression. Okay. So I have 2 variables. What are they? A and B. Okay. Now I have a function with 3 product terms. How many product terms? 3. AB bar plus A bar B plus A bar B bar. Okay. So look at this. Look at this truth table. A bar B bar is a function, is a variable in the function, so I am putting it as 1. A bar B is also a function, I am putting it as 1. AB bar is also a function, I am putting it as 1. So this is the truth table for the given function. And how do I do the K-map for this? I have 3 ones. For 0, 0, 0, 1, 1, 0, I have 3 ones. Okay. So I am placing 0, 0, 0, 1 and 1, 0. This is your second step. Once I am done with placing, what did I tell you? We'll go for grouping. Once I have done placing, we'll go for grouping. Grouping of 16. I have only 3 ones here. So 16 is not possible. 8 is not possible. 2 is not possible. So I have to go for group of 2 only. Okay. Now how do I do grouping? Grouping in either vertical way or horizontal way, but not diagonally. Okay. Please remember, if suppose I have 4 cells like this, okay, I cannot group them like this. This is wrong. Okay. So if I have ones placed like this, I can go for either horizontal grouping or vertical grouping, but not diagonal grouping. Diagonal grouping is not allowed, only vertical grouping or horizontal grouping with 2 variables, 4 variables, 8 variables or 16. Okay. Now when you look into this, I don't have 16 variables or 8 or 4. I have only 2 grouping combinations. Okay. So first I'll group this with this. This is one grouping, and next I have one more one here, right? I can't leave it like that. So what I do is, once I am done with this blue grouping, okay, when I have this one left out, I will group this with this particular number. So I have 2 groups which are formed. Okay. Now what do we do next? Okay. So as I told you, after we are done with this grouping, we will generate the expression for the given groups. Okay. Now here to generate the expression for the given group, we usually use some rules. Okay. So one is by combining the terms, or other is by combining the 2 terms. Okay. Now here the expression would be, look at this. So when I have these 2 things grouped, okay, so I will rule out this and this. So I will have only B bar left. When I group this particular thing, I will left out this and this, I will have only A bar left. So my expression would be A bar plus B bar. I know it is confusing. Let me repeat. The output of this blue grouping, would be B and B bar are complemented. So both of them will be crossed mark. So the output of the blue grouping would be A bar. Okay. When I take this red one, A and A bar are complemented. So I cancel this and the output would be B bar. So as I am taking min terms, I add them. As this is SOP, I add them. So the output of this blue group is A bar. The output of this red group is B bar. So the final expression is A bar plus B bar. Okay. Now the original expression had three variables, right? Sorry, three product terms with two ORings, but the reduced expression has only two literals with only one ORing. Okay. So A bar plus B bar is the reduced expression. Okay. Now look at this. Let me explain you once again. A and B, right? So when you have A and B here, 0, 1, 0, 1. So when for this particular thing, B and B bar gets complemented, so it will be cancelled. So the only option in this particular grouping is A bar. Okay. Now when I look into this particular thing, A and A bar gets cancelled because this is grouped like this. A and A bar gets cancelled, B bar is the option. So as I am taking SOP, as I have considered once in SOP, my output expression will be A bar plus B bar. This is your reduced expression. Okay. Next. You will understand it once we proceed further. Okay. Yeah. Next, solving POS. Okay. When I take the same POS variable, look at the difference. I am putting what? The added terms, and instead of ones, I will consider zeros inside the cells. I will do grouping of zeros instead of grouping of ones. That is the only difference. Okay. So you have to consider the added terms and you have to group zeros instead of ones when you take POS expression solving. Okay. Next. Okay. Now, when we go for 3 input variables, okay, this is all about 2 input variables. We will try to solve more and more problems in the next session once we are done with the basic concept understanding. Okay. Once you understand the concept, guys, we will go for more problems. Okay. Now, when you go for 3 variable, this is all about 2 variable K-map. When you go for 3 input variables, okay, we will have 2 power 3, that is 8 cells. Right. So I'll arrange 8 cells like this. Okay. So here I'll put A, B, C, 0 and 1, 0, 0, 0, 1, 1, 1, 1 and 1, 0. Okay. Please make a note of this. We are not putting 1, 0 here. We are going with grayscale coding. The 2 variable numbers should be adjacent to each other. So we go for grayscale implementation of representation in the cell arrangement when we go for K-maps. So instead of putting 1, 0 and 1, 1, we will put 1, 1 and 1, 0. So this will be 0, 1, 3, 2, 4, 5, 7 and 6th cell. Okay. So this is how we arrange the cells in a 3 variable K-map. Okay. Now when you are going for min terms, 0, 0, 0 is nothing but A bar, B bar, C bar, A bar, B bar, C, A bar, B, C and all that stuff. Okay. You just have a look at how did we arrange a 3 variable K-map. Back. Okay. Now look at this example of 3 variable K-map. Okay. Now I am taking SOP functions here, right? So look at this first one, f is equal to summation of 0, 4. What do you mean by 0, 4? 0th cell and 1 cell. As I have taken summation, that represents SOP and they are min terms. Please remember, this summation represents, that is in SOP form, and the terms inside that are min terms, hence I represent with ones. Okay. So how do I do grouping for that? I will just go for this group. Okay, only one grouping is possible. And what would be the result of this group? The 0 and 1 will be crossed mark and the output of this group will be B bar, C bar. So summation of 0, 4 is equal to what? B bar, C bar. How did I get that? 0 and 4 are placed, the min terms are placed. As this is grouped, this A and A bar gets crossed, the result will be B bar, C bar. Okay. Now let's look into the second one, 4 and 5, 4 and 5th cell. Okay, this is grouped this way. So when I go for this grouping, I have only one literal A here, I will take this. When I see this B and C, C is 0 here, 1 here. So C will be crossed off, so I will be getting A bar, sorry, I will be getting A, B bar. See, B is 0. Here also it is 0. C is 0 here, 1 here. So, C gets cancelled. So, the resultant will be B bar. So, my answer would be A, B bar. Okay. Now, when I look into this, I have 4 minterms here, 0, 1, 4, 5. Okay. All the 4 minterms are together. I can go for 4 grouping. Please do not do grouping of 2 here. What did I tell you? Check for 16 possibility, if not 8, if not 4. So, is there a possibility of 4? See, here in the earlier 2 cases, I didn't have 4 variables. So, that is the reason I have done grouping of 2 variables. But here in this case, I have these 4 variables adjacent to each other. So, I will go for grouping of 4. Got it? Don't go for 2 grouping. What will happen if I go for 2 grouping? I will get 2 terms. If I go for 4 grouping, I will be getting only 1 term. Okay. So, what would be the result of this? 0 and, see, this is occupying these 2 rows where 0 and 1 gets cancelled. It is occupying these 2 columns where C and C bar gets cancelled. So, the resultant would be only B bar. Okay. As B is 0, B is 0 in these 2 columns, my output is B bar. Okay. Now, look at this 0, 1, 2, 3. So, can I go for grouping of 4 because all 4 are adjacent? Yes. So, this is the grouping. So, when you go for this grouping here, 0, 0 gets cancelled with 1, 1, 0, 1 gets cancelled with 1, 0. They are complement to each other. Hence, the resultant is A bar. Got it? Next, look at this grouping 0, 4, 0, 4. Okay. But here, what is the difference here? Can you find out what is the difference? What is the difference here? 0, 4. Okay. Is this 0, 4 or 1, 3? Correct. Okay. So, this would be 1, 3, for which when you look into 1, 3, what will happen? This is this row A, and here B and B bar gets cancelled, C will be the variable. So, I will have A bar C. Okay. Now, let us look into this 4, 6. This is 4, this is 6. Okay. Now, here I would like to tell you one thing. Okay. Grouping can be done with the adjacent terms, right? Even if the K-map is like a round structure, even you have to consider them even if they are folded. Okay. Now, look at this. This is 4 and this is 6. When you fold it like this, even they are adjacent. So, I go for grouping of 4 and 6 this way. Now, what would be the expression for this? A is the only term, so I will take A. But when you look into 0, 0 and 1, 0, what is happening here in 0, 0, 1, 0? This 0 and 1, B term gets cancelled and C will be taken as C bar because both of them are zeros. So, A into C bar. Okay. Now, let us look into this 0 and 2. 0 and 2. I am folding it this way. So, this will be A. B and B bar gets cancelled, it will be C bar. A bar, as this is the first row, it is A bar. B and B bar are getting cancelled and I have 0 for C, hence it is C bar. Now, when you look into this, I have 4 variables on these 4 corners. So, what do? I go for 4 grouping, 4 variable grouping with this folding. So, what will happen here? 0 and 1 gets cancelled because this is covering these 2 rows, and when you look at these 2 terms, B and B bar gets cancelled, only C bar will be available. Hence, C bar is the answer. Okay. So, this is all about your K-maps. Okay. Don't worry, we will see about how do we do grouping. We are just done with 3 variable. We will see 4 variable, 5 variable, and we will also see more problems on how do we solve K-maps.